The first one we'll talk about is dispersion. These are the weakest of the intramolecular attractions. Now, dispersion is a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make the atoms form very temporary dipoles. So these are very, very brief, instantaneous, boom attractions just that last for a very short time, very temporary. I'll give you an analogy, then I'll give you a real example. So, for instance, if you guys are in your bus on the way to service, okay, and you're looking out the window, and then, hey, look, we drive by and we see a Brother Rice boy. He's got a football and he's got a helmet on. So you just drive by very quickly, and just for that a moment, that second you drive by him, there's that attraction. Oh, Brother Rice boy. So just, boom, really short, because you're just aligned perfectly as your window passes him. And he sees you in the window, and it's like just that one little bit, and then it's gone. And then you go back thinking about looking at the trees and stuff. But this dispersion is very, very temporary. Neon is happy. It's got 8 electrons. There's like no way it wants to do anything, right? So we have these 8 electrons around it. But we know that if something is in a liquid state, that there's got to be some interaction between those molecules. Water is a liquid, and there's interaction between water molecules that make it sticky with each other. Well, if we cool neon down enough, if we make it cold enough, neon becomes a liquid, and that means it will stick together. Now, what is the deal with that? Well, it has to do with dispersion forces, and let's look at the reason why that would happen. We have these 8 electrons, but they're not on the side of a letter N and a letter E. Remember that they are in clouds. So these ions, these electrons, can be really anywhere within that cloud. And on this one, we have maybe like 8 electrons over here. Okay, they're buzzing around. We don't know exactly where they are. So notice that if we have more electrons over here, in this area, it's going to be a little bit of positive, negative, just a little negative. Not much, just a little negative. And I can't seem to draw a negative. This new pen, I got to calibrate it. I was all excited. Okay, so it has a little negative. And now, since all the electrons over here on the right, this part's going to be a partial positive. And hey, look, lo and behold, for that instant, while these are over here and while these electrons are over here, there's going to be an attraction just for a second. Or not even a second. I can't even say a second, just even shorter than that, just for a snap, less than a snap. Boom. And then these electrons are going to go over here, these electrons are going over here, and there's going to be another neon. So very, very short-lived. But the important thing is these are going on all the time, very short, going on with neighbors here, neighbors here, neighbors here. So because of that, you're going to have very short-lived attractions. Very, very weak, though. Like when you're driving in the bus, that attraction between you and the Brother Rice boy, that was just very, very short-lived. Here we have nonpolar molecules, and because the electron clouds are the electrons are moving around all the time, we have partial positive, negative here, partial positive here, and the partial positive with the partial, and actually it shouldn't even say partial positive, just very slightly instantaneous positive, instantaneous negative, just very short-lived, as opposed to the dipoles, which we'll get to. These are just changing all the time. Let's continue with the van der Waals forces. We have dipole moments, or dipoles. So di means 2. So that's when polar molecules are attracted to each other. We talked about how in a polar covalent bond, one atom will want the electron more than the other if there are different electronegativities. thus creating a dipole, or two poles, a positive and negative pole. And when a positive and negative pole are created, with neighboring atoms, we have a slight attraction. Okay, that's a van der Waals interaction. Because of the electronegativity difference, one's going to have more of the electron, one's going to have less of the electron, and with a neighboring particle, a neighboring atom, there's going to be a slight attraction. Now, if we think of atoms as being bonded pairs, we can think of that as couples too at a dance club or just a dance. And you'll see this too if you watch closely. We have these couples, they're like bonded, they're going steady. We have Drake and Miley Montana or Hannah Cyrus dancing. They're a couple, they're bonded together as a couple. We have Selena Gomez and Justin Bieber. They're also a couple. They're bonded together as a couple. We have Rihanna and Chris Brown. And actually, Chris Brown was a student of mine in California from 2004 to 2005. It wasn't this Chris Brown, but his name was Chris Brown. And there was a girl in the class who loved the singer Chris Brown. She just talked about him all the time. She had pictures of him on her folder and everything. But the Chris Brown in my class used to think she was talking about him, and it was just kind of funny. He used to always lean back in his chair thinking, yep, I'm pretty cool. But he actually looked more like Isaiah Thomas than this Chris Brown, but it probably had to be there. So these couples here, what we have to realize, though, is it's not really an equal sharing of their partnership. Now, one, for instance, might be a little more positive, one might be a little more negative, might be a little more partial negative, this one might be partial positive. She could be partial negative, he could be partially positive. Now, even though they're bonded together, they still have a partial charge. They're not fully sharing their relationship equally. So what happens is, because there's a partial positive and partial negative within the couples or within the molecule, there's going to be a slight attraction. Look at Driz over here. He's checking out Rihanna. It's like, there's this attraction there. She's checking out Drizzy. And look at over here, Chris Brown, he's turning his shoulder. She's and with Selena. There's a little attraction there, a little attraction between Miley and Justin. Okay, so these are still couples here. Okay, doesn't mean they're not together. They're still together. They're still an item. It's just that, hey, they've got wandering eyes. She's looking at Driz. These guys are looking at each other. And the thing is, they're not just looking at each other, but on the dance floor, if, let's say, Drake moves to the left, he's going to take Miley with him, of course, because they're partnered. But Rihanna now, because she's somewhat bonded to him, she's got a dipole bond with him, they're going to move that way too, causing these guys to move as well. So everything's going to shift. They're all going to have this bond together. You'll see that they'll move as a group together, even though these guys are, again, they're bonded, but as a group, they'll move. They'll move together there. They're sticky. They're with each other because of the interactions, because of the attractions between the molecules. You'll see couples acting like this. Sure, they're dancing together, but this one's kind of overlooking his shoulder because of that little dipole attraction with another person. So next time you're dancing with someone and they have their head turned 180 degrees away from you, there's probably some dipole interaction with some other person at the next couple over. And if we look at this in chemistry terms, we have hydrogen and chlorine. We have a partial negative and a partial positive. So there is a attraction between these molecules here. Okay, sure, these guys are bonded, but there's a partial positive here, partial negative, so they have a dipole attraction, a dipole-dipole interaction. The strongest intermolecular attraction, a hydrogen bond. Now the hydrogen bond is extremely important in our life, in life itself. Your DNA is the double strands are connected by hydrogen bonding. Water has its properties, some of its properties, because of hydrogen bonding. Now, what's the difference between that and another dipole interaction? Well, it's much stronger. You have a hydrogen covalently bonded to a very electronegative atom. The fun atoms, nitrogen, oxygen, fluorine, the most electronegative, the most fun atoms there are. It's also weakly bonded to unshared electron pair of those electronegative atoms. So what are we talking about? Well, let's look at water, agua. That's water in Spanish. The oxygen is really going to want that electron much more. So it's partial negative. The hydrogen will be partial positive. Now also on those oxygens, not only do they pull more on those electrons, but they have those unpaired electrons. And we have the unpaired electrons here. It's partial negative, and really we should say it's partial negative twice. Partial positive, partial positive. Between these unpaired electrons, we have this hydrogen bond attraction. There's a hydrogen bond. It creates such a positive, partial positive region, and with the unpaired electrons and the partial negativity, we have somewhat of a pretty strong intermolecular attraction. Not as strong as covalent or ionic, but still it's pretty strong relative. Here we have the hydrogen bonds. So when hydrogen has a partial charge attraction to nitrogen, oxygen, fluorine. Now this what gives a lot of the properties of water. Water is sticky, right? You can have a big drop of water. Like if you're crying at a sad movie, you might have a drop of water just dripping right from your eyeball. That's not indicative of every single liquid. You try that with alcohol, it's not going to be that sticky. Okay, water will be very sticky. It sticks together very well because of hydrogen bonding. It's pretty cool. Here's another view of it. We have the intramolecular forces, the hydrogen bonds between the partially negative oxygen and the partial positive hydrogen. Okay, so they're kind of stuck, not strong bonds like this, but it's pretty much where you can drag a drops of water together because of those hydrogen bonds. Another view, we have the hydrogen bonds because of the partial charge. Partial positive of the hydrogen, partial negative of the oxygen. Pretty cool stuff. And together, all these hydrogen bonds create just the network of where we have all this water just stuck together. Now, it's not a super strong bond where we can't break it. We can break water, you just dive into a pool of water, you're breaking some bonds there. So they're not incredibly difficult to break, but they're pretty strong.